So our today's session is small signal operation of differential amplifiers. So we have discussed in the previous classes about the general MOS differential pair operation, how the MOS differential pair operates in the differential mode and in the common mode. And we have studied the large signal operation, that is what is the approximation for the signal where we can have a better linearity. So the signal VID input voltage, the differential input voltage should be less than the overdrive voltage. So that is the condition for small signal approximation. So with that, keeping in mind, we are going to continue with the small signal operation. We are going to have a lesser value of the input voltage VID. That is the small signal operation in order to have a better linearity of the operation of differential amplifiers. This is our circuit diagram. Here we have the differential amplifier Q1 and Q2. VG1 and VG2 are the input signal to the gate, and RD is the drain resistance, VDD is the supply voltage. VD1 and VD2 are the output voltage at the drain terminal. VOD, it represents the differential output voltage. So if we take the difference of VD2 minus VD1, we can calculate VOD. I is the constant current source, and we are having the negative supply V minus VSS. For the input signal VG1 and VG2, we are going to apply plus VID by 2 and minus VID by 2 for the both the transistors. And VCM denotes the DC bias, that is the constant DC bias that is required to operate the MOSFET. Okay, here we are going to take the VCM value as 0, the DC bias. Generally we give the DC bias to the gate terminal of the MOSFET, so that is why we are giving some DC voltage also here. Okay, so you can directly draw the small signal model. Okay, you can just write down the equation VG1 and VG2. So the MOS differential amplifier has input voltages VG1 and VG2. So VCM denotes the common mode DC voltage with the input common mode range of the differential amplifier. It is needed to set the DC voltage of the MOSFET gates. So it is typically at the middle value of the power supply. So here we are taking around 0 volt for the DC value. And the differential input signal VID is applied in a complementary manner. That is, we are going to give plus VID by 2 for the first transistor and minus VID by 2 for the second transistor. So these are the two input signals that is applied at the gate of the transistor. So I'll just give you a recap. See, till the previous analysis, see, initially we discussed about in general about a differential amplifier. We discussed what is a common mode operation, what is a differential mode operation. So in the differential mode operation, we are taking the we are giving the different input to both the transistors, and the amplified version of the differential output we are taking at the drain terminal. Whereas in common mode, we are going to give the same input to both the transistors, and similarly we are going to take the differential amplified output at the common mode output. So this is what we studied about common mode and differential mode operation. And large signal operation, we are just bothered about the input signal VID by 2. So this input signal, what will be the range of the input signal that should be given to the transistor? So here we finally came to a conclusion that this signal, it should be small, that is, it should be lesser than the overdrive voltage for the linear operation of the transistor. So that's what is the conclusion arrived in the previous large signal operation. Okay, so keeping that in mind, we are giving the value of VID by 2 lesser than the overdrive voltage in the small signal analysis, small signal operation. Okay, so from this we are going to calculate what is the common mode rejection ratio. So we are going to calculate the differential mode gain, common mode gain, and then calculate the common mode rejection ratio. So that's what we are going to do in this small signal operation. So this circuit, it is just showing the total VID, applied VID. So here previous circuit we have given, we have splitted this input voltage as plus VID by 2 and minus VID by 2 across both the transistors. So here it is combined. So VID is just combined, taking the two gate. Okay. So in the DC analysis, if you are going to take only the in the DC analysis, we are just going to give the DC input VDD. We are going to have ID1 and ID2 as I by 2 and I by 2. Okay, so the output voltage across both the transistors will be V0 and V.2, which is VDD minus I by 2 RD. And similarly, V02 will be VDD minus I by 2 RD. So these both we call it as single-ended output. So single-ended output means we are taking across single transistor. Okay, so this VOD represents the difference of V01 and V02, which we call differential output. So now when we apply AC signal, V01 and V02 will be riding on top of the DC voltage at the drain. That is when we are going to give the AC input, the ID1 and ID2 will slightly change depending on the input voltage. So the double-ended output V0 here will be, if you take the difference, this will be 0 volt. So if AC signal is applied, we will get V0 as an entirely signal component. So now this is during the DC analysis, the output voltage is, the differential output is 0. Now when we apply AC signal, let us see what happens. So now we are going to apply AC input. So this is plus VID by 2 and minus VID by 2. So you draw the circuit diagram. This is for the AC analysis. So here in this AC analysis, we have the gate terminal G1, input VID by 2 is given to the gate terminal of the first transistor, and gate terminal 2 G2, and minus VID by 2 we are going to give at the second transistor. So we are giving complementary input, and source 1, source 2, and across the drain terminal we are taking the output voltage V01 and V02, and we are taking the same value of the drain resistance. So ID1 and ID2 represents the output currents at the drain. V0 will be the double-ended output, or it is the differential output at the drain. GM VGS1, it's the constant current source on the input, on the output side. So VGS1 represents the gate to source voltage for the first transistor. Similarly, VGS2 represents the gate to source voltage at the second transistor. GM VGS2 represents the constant current source on the output. So now here we are going to calculate what is the single-ended, the output for the single-ended case and the double-ended output. That is, we are going to calculate the differential gain, basically the differential gain. Okay. Now this ID1, so this ID1 we can take the ID1 can be approximately, it is equal to GM VGS1. Similarly, ID2 it will be equal to GM VGS2. Right, ID1 is the current that is flowing at the output, GM VGS1, ID2 is GM VGS2. Okay, so what is VGS1? VGS1 is the voltage, that is input voltage that we are giving at the gate, from the gate to source. It is plus VID by 2 here for the Q1 transistor. Similarly, for the Q2 transistor, it is minus VID by 2. Okay, so now we are going to substitute in the drain current equation the value of VGS1 as VID by 2 and minus VID by 2. Okay, and then we are going to calculate the output voltage. Now, so neglecting the output resistance, each of Q1 and Q2 is biased at a DC current of I by 2 and is operating at a overdrive voltage of VOV. So here we are not taking the output resistance, effect of output resistance. So later, if we want, we can consider the output resistance. And so we are giving a bias current of I by 2. So the total current is I, it is divided as I by 2. It's the DC current and it's operating at a overdrive voltage of VOV. So we know that VGS1 and VGS2, it is the complementary input. And VID by 2, it is lesser than the overdrive voltage, which is the condition for small signal operation. So we have already set this VID by 2 to be less than VOV. Now we are calculating what is the output voltage at the first transistor. So the output voltage here, so you have the circuit, right? So the output voltage is calculated as the current into resistance. right? So this current is flowing in the negative direction, so we are giving this minus sign. So this ID1 now it is replaced with GM into VGS1. So similarly, V02 is again minus ID2 into RD. So now we are going to replace this ID as GM into VGS2. Now we are going to calculate, now we are going to substitute for VGS1. VGS1 we are going to substitute as plus VID by 2 and VGS2 replace with minus VID by 2. Next we are going to calculate what is the gain. That is this is the, if you calculate the gain, V0 by VID will give the gain. That is output voltage by the input voltage will give the gain. Now we are going to substitute VGS1 in terms of VID. So now we have replaced VGS1 with the plus VID by 2 and we have taken the VID term to the left hand side. So now this V0 by VID, it's the gain, the differential gain. So which is minus GMRD by 2. So this equation we have used in our differential amplifier design. Do you remember this equation that we have used? But we have used for the BJT case. So we have used GMRC by 2. So that is, this is the differential gain AD, which is GM into RC by 2. We have used for the BJT. So now it is, since it is MOSFET, GMRD by 2. This is for the single-ended output. That is when we are taking across a single transistor. So similarly, for the Q2 case, so when we are replacing with the, that is VGS2, we are replacing with minus VID by 2. So after that, this minus will cancel, and when we calculate the gain, it is GM into RD by 2. So this any one we can use. This is for the single-ended case, the output, the gain for the single-ended case. So when we take the difference, so this is AD, that is this V01 minus V02. If you take the difference, that will, then we can calculate the double-ended case. So now we are going to take the differential output. So when we take the difference, so we are going to have the gain AD. AD is the differential gain, which is V0 by VID. It is around, it is GM into RD. So take V02 minus V01 and it is GM into RD. So this is for the gain for the double-ended case. So this expression we have used in calculating the numerical. We did one numerical based on this expression in the previous class. So this is for the, if it is mentioned the differential output, then we have to use this gain expression. Differential output or double-ended output, we have to use this expression. So if it is mentioned single-ended output, we have to use GMRD by 2. The gain expression as GMRD by 2. The drain current increment of Q1 is GM VID by 2. Similarly, for the Q2, it is GM VD by 2, VID by 2. So need not take this. You take only the gain expression. AD equal to GM into RD.
Ma'am, if it's a differential output or a double-ended output?
Double-ended and differential output are one and the same. So now GM is the transconductance. So these equations, it is just shown for your knowledge. GM equal to 2ID by VOV. So this few students have got the doubt. GM value, either you can use I by VOV, the bias current divided by VOV, or 2ID by VOV. Okay, for the GM calculation. So now when we include the effect of the output resistance, okay, what will happen? So in the previous analysis, we have not considered the effect of output resistance. If we include, so the equations will slightly change. That is everywhere in all the equations in the RD, the drain resistance, you can add just the parallel in parallel with R0 if we are including the output resistance. So in some numerical, they would have mentioned that output resistance is included. So in such case, you can use this equation for calculating the output voltage. So similarly, if your gain will be GM into RD parallel R0. So you can take this expression for V0 expression. Next is the common mode gain. So the common mode gain, we are going to calculate, we are going to give a smaller input voltage VICM. VICM is applied at both the transistors. So here we are going to give a same input voltage to both the transistors. And here we have included another degeneration resistance from the source to ground. Okay, in the common mode operation. This resistance is included basically to reduce the linearity, means the distortion in the circuit. Okay, so now in the common mode operation, since we are giving same input voltage across both the transistors, here it is like a so it's a mirror. Okay, so we can take 1/2 of the circuit for the analysis. In order to reduce the complexity, we are going to take 1/2 of the circuit. We are going to divide the circuit into two and take 1/2 of the circuit and draw the small signal model, or the we do the AC analysis for the 1/2 of the circuit. Okay, so now we have divided 1/2 of the circuit. So now it is this 1/2 circuit you can draw. Okay, so the bias current is divided as I by 2, and this resistance RSS, it is divided as two resistance in parallel, 2 RSS, 2 RSS. So we are writing 2 RSS for the 1/2 circuit. Okay, so draw this circuit. So when a common mode input signal such as a disturbance or interference signal is applied to both the terminals, it performs common mode operation. So because of symmetry, the circuit is divided into two halves. Each half is called as a common mode half circuit, which is biased at I by 2. The source degeneration resistance 2 RSS is included and effect of R0 is neglected. Now we calculate the common mode gain, which is either V01 by VICM or V02 by VICM. So if you consider any one of the transistors, we can calculate the common mode gain. So here is our equivalent circuit. So for the 1/2 circuit, this equivalent circuit is drawn. So from this, we are going to bring the expression for the gain. Okay, take the circuit. So if you see the equivalent circuit, we are going to give the input voltage VICM at the gate terminal, and RD is the drain resistance at the drain. V01 is the output voltage that is taken at the drain terminal. ID is the drain current, and VG1 represents the voltage at the gate. So GM VG1 represents the constant current source at the output, and from the source to ground we have the degeneration resistance 2 RSS. So the same circuit, 1/2 circuit, we are drawing like this. Okay, so from the circuit we are going to calculate the gain. We are going to ultimately calculate V01 by VICM. What is the common mode gain? First, we are calculating VG1. VG1 can be written as, so this current ID into 1 by GM, that is the voltage is represented as, we are going to calculate what is the drop across this constant current source plus across this resistance. Okay, so here this voltage drop will be this current into this resistance. Here it is 1 by GM, which is inverse of the transconductance. So it is current into this 1 by GM plus this current into this resistance 2 RSS. So we are calculating the overall voltage VG1 as sum of the current into resistance of the current source plus this resistance. Now, so from this equation, we are taking this ID in common, and then this 1 by GM into 2 RSS, we are taking it outside, and we are rewriting in the form of the drain current. So we are taking this total expression to the denominator on the left side, VG1 by the resistance term. So this current equal to V by R. Need not write this, you take the final expression. Okay, just try to understand the flow. Okay, so next we are going to substitute the ID value in the output voltage. That is the output voltage we can write as, this output voltage can be written as minus ID into RD. We are going to substitute for the drain current, which is obtained from this previous equation. So this equation we are going to substitute in the output voltage. we are going to substitute here, and here from here we are going to bring VG1, the input voltage, on the left side. So V01 by VG1, it will give you the gain. So this is minus RD by 1 plus GM into 2R plus 2RS. So this expression please write down, because when we calculate the gain in some numericals, this 1 by GM effect will be neglected, and some places we will consider 1 by GM effect. Okay, so generally this 2 RSS is far greater than 1 by GM. So the effect of this 1 by GM is negligible compared with 2, because transconductance is very high. So if you take inverse, this value is negligible, so we can neglect. Okay, so we are left with the minus RD by 2 RSS, which is the gain expression. But in some cases we may consider the effect of the transconductance. So this total expression you have to use for the gain calculation, or else it is just a minus RD by 2 RSS is the common mode gain for both the transistors. So since we are now analyzing only one half, this is going to be the same for this other half also. So V02 by VICM will be same as V01 by VICM, which is minus RD by 2 RSS. So now this is for the single-ended case, the gain for the single-ended case. So what will happen for the differential output? Or the double-ended case, what will be the gain?
Minus RD by RSS.
Minus RD by RSS.
No, if you just take the difference of the both, it will cancel, no? It will be 0.
Yes, ma'am.
This is for the single-ended case. AICM represents the gain for the single-ended case. For the double-ended case, if you take both, minus of minus will cancel, which is 0. Okay. So the common mode rejection ratio, we are representing, we are calculating the. So have you taken this expression? AICM equal to minus RD by 2 RSS. So next we calculate what is the common mode rejection ratio. So we have already discussed about common mode rejection ratio. It's the figure of merit for any differential amplifier, which indicates the ability to reject the interference or the common mode signals. So the measure of effectiveness of the differential amplifier in amplifying the differential mode signals and rejecting the common mode interference is the ratio of the magnitude of the differential gain to the common mode gain. So we are calculating CMRR as differential gain by the common mode gain. So now we have calculated two cases, single-ended case and double-ended case. So CMRR will change for both the cases. So now we are just recapping for the single-ended case. For the single-ended, ACM represents this, the gain, which is if you take the magnitude, the negative sign will be removed. So it is RD by 2 RSS. And the common differential mode gain, if you take the magnitude, it is GMRD by 2. So you have already, I told you to note it down. So this is for the single-ended case. So if you are going to substitute this in the CMRR equation, so we are just calculating the CMRR. So GMRD by 2 by RD by 2 RSS. So the common terms will get cancelled, and finally our CMRR expression is GM into RSS. So this one you noted down. This is for the single-ended case. CMRR for the single-ended case.
Ma'am, once can you just explain what is common mode rejection?
Common mode rejection ratio is the ability or the effectiveness of the amplifier. Okay, in amplifying the purpose of the differential amplifier is to amplify the differential mode signal and reject the common mode signal. The common mode signal will be interference or noise. Okay, it has to cancel the common mode signal. So that's why the common mode output is very less. Okay, it is ideally 0, and differential mode, it is the amplified version of the differential signal, which is an old scale. Okay, and CMRR should be high, generally high. The higher value of CMRR, the performance of the differential amplifier is good. It's the figure of merit for the differential amplifier. So now can you calculate for the double-ended case? So for the double-ended case, ACM is zero.
Zero. Infinite.
Yeah, AD is GM into RD. So if you take the ratio, CMRR will be infinite. So for the double-ended case, CMRR is infinite. Next, this is true when the circuit is perfectly matched.